Hello and welcome to another video by Adrian from Pure Electric. In this video, I'll be discussing some of the basic knowledge and considerations that I believe are required for you to perform safe isolation correctly and avoid anyone receiving an electric shock or damage to tools and equipment. Before we can gain access to live parts, we have to satisfy the Electricity at Work Regulations 1989 and using the guidance set out by Electrical Safety First Best Practice Guide 2. Guidance on the management of electrical safety and safe isolation for low voltage installations, which is available for free from Electrical Safety First online. Just click the link on the screen. This is what Electrical Safety First Best Practice Guide 2 suggests on page 5. And as you can see at the bottom, it clearly states that all three conditions must be met in order for work on or near live conductors to be carried out. These regulations may be due an upgrade as they appear to be suggesting that all electricians may be male. I'm sure it's just a typo, but it just goes to prove that people don't read these regulations, as this is the first time that I've noticed it myself, and I've not heard anyone else mention it before. It also references that HSE, Electricity at Work Regulations 1989, Regulation 14, which also has the same typo. To comply with Regulation 14, work on or near live conductors, dead working should be the normal method of carrying out work on electrical equipment and circuits. We can comply with this regulation by safely isolating the live conductors at various points within the installation before we gain access to them. In the majority of situations, there should not be many reasonable circumstances where the installation should be live, but every job should be taken on its own merits. So why is safe isolation so important? Well, firstly, there are the legal reasons. And if you ever ended up in a court of law, you would have to prove beyond all reasonable doubt that what you did complied, and there may even be a panel of specialists trying to prove otherwise. This is where Regulation 29, the defence regulation, comes into play. It also references Electricity at Work regulations in BS 7671 at the front, and it states that if you comply with BS 7671, you comply with the Electricity at Work regulations. Ultimately, in the real world, it's your call, but for your training assessments, you have to comply, and I wouldn't take any shortcuts that you have been shown on site, as this could prove costly for your assessments. Ask yourself why these laws exist. The answer is to protect people from themselves or from other incompetent people. So what are the dangers from electric shock? When I talk about this at work, I always put this question to the room and ask them to put their hands up. It never ceases to amaze me how many people think that getting an electric shock is part of the job or a risk worth taking. And some even think it's funny and brag about how many electric shocks they've had or how many pairs of new cutters they've had to replace because they keep blowing them up. When I ask people why they don't perform safe isolation, I hear excuses like, we don't have time. My boss doesn't do it. No one does it. One guy was even told that if he got the safe isolation kit off of the van, he would be thrown off of site. So this leads me to believe that we have an institutionalized complacency to the dangers of electricity, which is putting people at risk. Your employer could argue that you don't need a safe isolation kit because they are in charge of the installation. And while that may be true, they still have obligations under the Electricity at Work regulations and still need to perform safe isolation for any circuit that is being worked on. I would argue even more so for persons under their supervision, as they are the duty holder, and it would not look favourably in court if they failed in that duty. For you, you have to ask the question, are you happy to put your life in the hands of someone else? Look at Regulation 13, for instance. This regulation therefore requires that adequate precautions are taken to ensure that conductors and equipment cannot inadvertently be energized while the work is taking place. This is the process of safe isolation. By now, you must have seen how easy it is to receive an electric shock or blow your cutters up. All it takes is a split second of misjudgment and someone could die, and it could be you. So my next question at this point is, what do you think saved you? I've already shown them this picture during their induction, so I'll remind them that the sensation of electric shock may only be 1 to 2 milliamps due to the impedance of the body. And had they been holding onto a zero potential on the other hand, the current could have gone directly across their heart, potentially causing death. A current of as little as 0.007 amps or 7 milliamps across the heart for 3 seconds is enough to kill. 0.1 amps passing through the body will almost certainly be fatal. Other factors that can determine the severity of an electric shock include the duration of the shock and where the shock enters the body. For example, a shock passing from one arm through your chest to the other arm is more dangerous as it goes across your heart rather than a shock between two fingers. This extract is from 1966 Journal of the American Physical Therapy Association, and I want to draw your attention to this passage here. While any amount of current over 10 milliamperes, 0.01 amp, is capable of producing painful to severe shock, currents between 100 and 200 milliamperes, so 0.1 to 0.2 amperes, are lethal. Currents above 200 milliamperes, while producing severe burns and unconsciousness, do not usually cause death if the victim is given immediate attention. Resuscitation consisting of artificial respiration will usually revive the victim. This just goes to show how serious the situation really is and why lone working around electricity carries a much higher risk. So again, I suggest to you that if you're being left in charge of jobs while your employer leaves the building and goes elsewhere, you need to be in control of the electricity and ensure that it is switched off and isolated, because if there is an accident, there won't be anyone there to revive you. So once the electrons penetrate your skin, your body contains different impedances through each body part. And if you were to become part of the circuit, then electrons would start to flow through your body, causing tissue damage. Your body is also controlled by small electrical impulses. These are disrupted and overridden, which can be detrimental to your bodily functions. For example, stopping your heart from beating, your lungs from working, as well as heating up the flesh and literally cooking you, and potentially destroying your body's cells with short-term effects and long-term consequences to your health. You also see from this table that as voltage increases, your body's impedance, which is the resistance your body has to the electron flow, decreases, and there is only a 75 ohm difference between 225 volts and 400 volts. If you're interested in this article, the link is at the top of the screen. BS7671 also states that the touch voltage should not exceed 50 volts, as this is where the voltage is strong enough to push electrons through your skin more easily, which is why we use RCDs to limit the current in a full condition. On page 64, regulation 411.5.3 gives the formula RA times I delta N is equal to or less than 50 volts. If you then take a look at table 41.5, you will see that they have already calculated the maximum current in milliamps and the resistance you can have before that 50 volt touch voltage is reached. It's also worth noting that if your skin is wet or you have a cut, then that touch voltage can be dramatically reduced as the barrier your skin provides is no longer intact, so it could take less voltage to break through the impedance of the skin. Even if you didn't receive an electric shock directly, you may have blown your cutters up. Due to the low resistance of the metal, the current would have been able to flow unimpeded and to a much higher level before the overcurrent protective device would have operated. We will talk more about this in subsequent videos within this series. So thankfully for you and your family, you are hopefully holding insulated tools, which according to the hierarchy of controls would come under PPE, the least effective form of protection. As it's the least effective method, it's classed as your last line of defense, and you should only be using that to minimize any further risk once the more effective methods have been implemented. Which begs the question, what caused the hole in your cutters and how much current was flowing? The easiest way to describe this is to consider arc welding. Essentially, when you are arc welding, you are putting an electric current through a piece of wire. That current will melt that wire with the metal you are welding into a molten pool of metal. And that is what happened to your cutters. The amount of electrons flowing through your cutters was enough to turn the metal molten and even vaporize it. So how much current would it take to do that? Well, here is a quick look at the supply current to give you an idea of why we need to protect people from electricity. We will cover this in more detail in the subsequent videos as we work our way through the testing process. But as you can see here, I've used 230 volts as my baseline voltage, along with a TNCS earthing system, which the on-site guide suggests should have a maximum external resistance of 0.35 ohms. The lower this figure is, the higher the potential current that is available in a fault condition. We then divide 230 volts by 0.35 and we get a current of 657.14 amps, or roughly 0.66 kA on your multifunction tester. In this table, you can see that when the resistance goes down, the current goes up, exactly like you were taught at college. As the resistance starts to drop below 0.15 ohms, you can really see that current jump exponentially. Effectively, the closer we are to the local transformer, the lower the resistance in the supply cable and the higher the fault current available. Now, the question you have to ask yourself is, do I want myself, or anyone else for that matter, to be connected to that amount of current? And hopefully the answer is a firm no. You are being paid to do a job, and that includes safe isolation, and not only keeping yourself safe, but those around you. If you haven't been given enough time to complete the job safely, then the job failed before you even got there. Your responsibility to ensure that whoever made that mistake is the person who feels the pressure, not you. The two things that get cut on site when there isn't enough time are health and safety and inspection and testing. If you keep covering up their mistakes and cutting corners to make the job achievable, ultimately you are bailing them out by putting your life at risk. You have to ask yourself, would they do the same for you? What is the safe isolation process? Here I have a slide that I teach the apprentices, and I've given some examples to help you during safe isolation. Elimination is always the most effective means of protection because if there is no hazard, no one can get hurt. It's as simple as that. We can substitute high voltage for low voltage, and 50 volts is considered to be your safe touch voltage, which we have discussed. Engineering controls are implemented to stop people interfering with your safe isolation process, and the admin controls are RAMs, signage, notifying people of procedures, working out of hours, and ultimately who is taking responsibility. Finally, we have PPE, which again is your last line of defense when all the other controls have failed, or as a way to lower any remaining risk after a risk assessment has been carried out. Here is an example of a basic safe isolation kit. This kit is comprising of a voltage indicator complying with BSEN 61010-031, or in this instance, BSEN 61243-3, a proving unit capable of showing the full range voltage for the circuits that you are working on, a lock with a unique key that only you have access to. Try and get a long one like this, as it will be long enough to fit through rotary isolators, etc. A warning label that shows other people who is in control so that they can contact you if they need it removed. If you think about it, someone might be tempted to interfere with the device if they have no idea who it belongs to and it's stopping them from working. The longer it goes on, the more dangerous the situation is going to become because they're going to get frustrated and more anxious to get going. You'll also need a selection of toggles for a range of devices, so try to get a decent range. The multi-clasp at the top is for multiple people to put their lock into, and when the last person has removed their lock, only then can the circuit be energized. If you take a good look at HSC's publication GS38, and I suggest you do because it'll be in your exams, it will describe and detail the level of protection that your voltage indicator should achieve. Here are a few brief points. Again, it needs to conform to BSEN 61243-3 and displays the installation category, so whether that's category 2, 3 or 4. The probes and tips need to be 2 to 4 mil maximum for the metal that is showing. TIS 859 comes with retractable tips that are replaceable. It needs to have finger barriers to stop you from slipping into the live terminals as you're pushing the test into them. Insulated and durable leads that won't get damaged easily, the manufacturer's name, and possibly even a high breaking capacity fuse and or current limitation. For those of you that don't know, current limitation is where the internal resistance is so high that current cannot flow easily. This protects you from having a highly dangerous probe tip waving around when the other probe is connected to the line terminal. The guidance set out by Best Practice Guide 2, Issue 3, is that you should preferably test your voltage indicator safely on a dedicated proving unit like this one, rather than accessing live terminals. It also suggests that electricians who work on installations or regularly work on installations that have been energized should have one, and even those that only occasionally work on installation should have one too. Electrical Safety First have also brought out further guidance on the limitation of plug-in devices such as socket testers, as they are not suitable for safe isolation. A lot of people miss the key information on the front of the unit as they are not capable of picking up a neutral earth reverse. The Best Practice Guide 2 also advises against the use of voltage sticks for safe isolation purposes as they are not reliable or accurate, and their use as such has caused accidents. It is worth noting that non-contact voltage indicators can be useful for identifying if a cable is potentially live without having to gain access to live parts, but that if the stick does not illuminate, you cannot assume that the cable is dead and should instead continue to proceed caution and assume that it is live until proven otherwise. Although cables with a metallic sheath, for example FP, SWA or SY flex, can shield the volt stick from picking up the electric field required to make it work, so it may not be suitable for those cables. They are also handy for identifying if a Class 1 metallic accessory or enclosure has been earthed, as they will illuminate when touched against the enclosure. So let's put that into context in the real world. If you were, for instance, about to move a washing machine or dishwasher, a metallic washing machine or dishwasher, which is a Class 1 accessory, and you're about to pull it out, the first thing that you would do is you would put your volt stick against it. If it illuminated, that would mean that the device is not earthed correctly, okay? And that will help you make a judgment as you're pulling the machine out, obviously isolating it first. Best Practice Guide 2 also quotes the following: the Electricity at Work Regulations 1989 definition of isolation is given in Regulation 12 and means the disconnection and separation of the electrical equipment from every source of electrical energy in such a way that this disconnection and separation is secure. In effect, this means not just cutting off the supply, but also ensuring that the means of disconnection is secure as described in this guide. In most instances, this will require securing the means of disconnection in the off position, and it is highly recommended that a caution notice or label is posted at the point of disconnection as described in the guide under Safe Isolation Procedures. As you can imagine, electrical tape does not qualify as a secure device. It can easily be peeled off or fall off, which means that someone else can easily be in control of your electrical installation. If someone else were to energize the installation and there was a death as a result, being the duty holder, you would be the person who could be prosecuted. I've then put this flowchart together to help you understand the thought process for safe isolation. The first thing we do is to prove that our test equipment is to GS38 and that it works correctly. If not, then you either replace or service the test equipment and try again. The reason I suggest proving this unit works first is to minimize the time between seeking permission, isolating the device, and proving dead. This is the point where the process is most vulnerable, as you may have covers off and more things can go wrong. Next, we locate the circuit or equipment to be worked on, as well as the point of installation. The guidance from the Best Practice Guide is to prove that the equipment is actually controlled by the isolation device and not just to assume that this is the case. You can do that by operating light switches or plugging in a socket tester. But the best way is to use a circuit finder, like the one pictured here, which costs around £100 inclusive of that. If you come across an unknown circuit, you must assume that the cable is live until proven otherwise, even if it is marked up as dead or not in use. The Best Practice Guide 2 suggests that a clamp meter can be a means of identifying a cable, but that will only work if current is flowing, so it suggests using cable detection equipment with a signal generator. When we seek permission to isolate, we need to minimize the time between permission being given and the circuit being isolated. If you think about it, what will people start doing if too much time elapses? Well, ultimately, they'll start work. I would suggest giving the responsible person a time of around 10 minutes between asking for permission and the power being cut. This will give you enough time to let people know and make preparations. Obviously, that is site dependent. The bigger the site, the more time that you'll need. Another little tip that I suggest is to offer to get the apprentice to stick the kettle on. And that way, when the tea is ready, everyone comes to a natural stop and you can switch the power off without argument. Once we have permission, we can operate the isolation device and fit our locks and warning labels so that we can safely test. Once the lock and toggle are on, give it a firm tug and wiggle to ensure that no one is able to interfere with your control. I cannot even begin to tell you how many times I've been assessing and I've been able to gently knock the toggle off because it was never on properly in the first place. Don't forget that it's traditionally 3 tests on a single phase circuit and 10 tests on a 3-phase. A lot of people get caught out when testing a lighting circuit as they forget to operate the switch and test the switch lines. So I've put this in as a step so that you don't forget it. If the circuit is not dead, proceed with extreme caution. You could now be in a very precarious position as you have access to live parts. Carry out a risk assessment, close off the live parts again and repeat the process. Again, I would highly recommend purchasing a circuit finder like the one I showed you before. This will increase your chances of being right and not making a costly or deadly mistake. Well worth the money to look professional and avoid unwanted circuits being isolated. If the circuit was dead, you now need to reprove your voltage indicator. Again, consider this. How would you know if the tester was working properly? Because the circuit was dead, so no LEDs would have lit up. Either that, or your voltage indicator developed a fault while you were using it, and this is what you need to do to prove that it worked one last time. If the device is working, you can begin work. If not, you need to carry out a risk assessment, make safe, and then replace or service your test equipment, possibly even starting the process again. A big problem for a lot of apprentices is where they should actually isolate from. When performing safe isolation, you need to consider what accessory you are isolating and ensure that you are isolating upstream so that you remove any sources of energy as you gain access to live parts and basic insulation within an enclosure. Here, I have drawn up a very basic flow diagram showing the supply coming in from a local transformer, the type that you would find out in the street, perhaps in an enclosure like this one or behind a fence with warning signs posted around the perimeter. Next, we have the service head, which houses the main fuse and is usually controlled by the local distribution network operator or DNO. These are usually sealed with a metal crimped tie to avoid tampering. I've left the electricity meter out for clarity, but this would usually go between the main service head and the consumer unit. If you look at the first few pages of the on-site guide, you will see the traditional arrangement. After this, we have a double pole main switch. You need to check whether this can be switched off under load. I will talk about that at the end of this slide. And this then leads to the single pole MCB or RCBO that is protecting the circuit. The appliance is connected to the circuit via an isolator, which in this case is a 13 amp plug, and this socket is only single pole. Although double pole ones exist, and I would highly recommend using one of those. They are more useful having a neutral, which can be isolated when you have a neutral earth fault and the RCD is tripping out. Finally, we have the load, which in this case is a washing machine. In order to be able to work on the washing machine for mechanical and electrical maintenance, you need to be able to disconnect the appliance from the supply to prevent accidental energizing. Ideally, this isolation should be local to the appliance to enable low-skilled or non-electrical workers to work safely. If I then add in the enclosures for each point, we can start to look at the supply and load side of each point of isolation. Hopefully, once you start to understand this, it will make safe isolation easier for you to understand and the reasons why you isolate upstream when gaining entry to an enclosure. Here we have the supply coming into the enclosure, originating from upstream, and the load coming out of the enclosure and heading downstream to the next enclosure. Just remember the source or supply is always upstream, just like the flow of a river. As we move downstream, what was the load from the previous enclosure is now the supply to the next, and the load is always coming out of the enclosure downstream. As this continues, as we move downstream, the supply is upstream and the load is downstream. Same again, supply is upstream, the load is downstream. Finally, we get to the end of the circuit, which is usually the appliance or point of load. Let's imagine that we want to gain access to the load. As the appliance is not working and the socket is, so we want to check the electrical connections. Before we can gain access to live parts, we need to think back to the hierarchy of controls. The most effective method to protect us from a hazard is elimination. The hazard in this instance is electricity, and we can remove that hazard by isolating the supply to the appliance. We need to look upstream to isolate the supply, which means we are looking at the single pole isolator, in this instance, the single socket. We could be thinking that isolating the switch would be sufficient, as this would remove the electrical supply. But what would be stopping someone from operating the switch whilst we were working on the appliance? And it's worth noting that a switch on a socket is not capable of being locked off. So the best option is to unplug the appliance. What's to stop people plugging in the appliance, I hear you cry? Well, that's a good question. Unfortunately, there is an affordable piece of equipment from Martindale on the market for such dilemmas, and it's one of these. They also sell one for the appliance itself, and as do Master Lock. Let's imagine that it's the socket that needs checking or replacing. Again, we need to look upstream from the socket, and this brings us to the MCB. We can easily isolate this by operating the switch. But first, what are the hazards? Let's look back at the hierarchy of control. Well, someone else could be using the circuit and/or equipment that needs to stay on. So now that we have identified our point of isolation, we need to seek permission to isolate, which is our admin controls. Once this is given, we can now operate the MCB, and we can also secure it in the off position by using a lock-off toggle, like the device shown here. This fulfills the engineering controls and prevents people tampering with your control of the installation. All that's left to do is to prove that the socket has been de-energized, because there shouldn't be any supply to the socket terminals that LEDs won't light. So don't forget to prove that your voltage indicator is working correctly first. Otherwise, how would you know? Without this vital step, you will fail with safe isolation, as there is a slimmest chance that the power could still be on. The circuit is potentially de-energized and unable to be re-energized due to the lock-off on the MCB. We can initially test the socket front by plugging in a socket tester as a further check to test to increase our chances of success before we gain access to the live terminals inside the socket. I recommend buying a socket tester where all the LEDs light up, or it has a self-test, so that you know if one of the LEDs is malfunctioning. Once you are 100% satisfied that you can safely gain entry to live parts, only then can you unscrew the faceplate to test at the terminals with your GS38 approved voltage indicator. It's a good idea to put the test probe onto the earthing conductor first so that you don't have the other end potentially live. So put the probe first on earth, then test to the line conductor. Remove from the line conductor first, and then still with the probe on the earth, come to the neutral, remove it from both. As the neutral is safer than the line conductor, put one of your test leads on the neutral first, and then bring the test probe to line to test between neutral and line conductors. Finally, don't forget to prove that your test equipment hasn't malfunctioned during the test. Remember, how would you know if it was working, as the LEDs wouldn't have been lit? So you need to prove these again to ensure the circuit is 100% de-energized. Only then are you finally safe to work on this accessory. And the process repeats itself as we work our way through the circuit, with the exception of the consumer unit's main switch. Unless there is an external isolator between the electricity meter and the consumer unit main switch, you have no way of isolating the supply from the main service head, at which point you should contact the DNO and ask them to remove the fuse for you. For instance, this will enable you to change the consumer unit safely, and it would probably be worth putting an additional isolator between the meter and the consumer unit for future consumer unit changes before the DNO replaces the fuse. This may not be an option, and you may not be able to isolate the boards in the assessment at college, and particularly it's currently not an option for the AM2. This means that your only option is to go through the safe isolation procedure by seeking permission, switching off the main switch, and locking this off before gaining entry, so that the supply side of the main switch is the only thing that is live, before proving the load side of the switch is dead. It's also worth noting that the guidance from Electrical Safety First is that single pole devices are not suitable for TT systems or IT systems. Multi-pole switching devices capable of isolating line and neutral conductors should be used instead. So next time you're standing in front of a consumer unit or accessory looking to gain entry to the live part, don't forget to seek permission to isolate the supply, remembering that the main switch could be an isolator and not a switch, meaning that it may not be designed to be turned off under load. In this case, operating each individual circuit to remove the load and working our way to the main switch, we can avoid damaging the main switch. Then secure the main switch in the off position with a suitable lockout kit. Most three-phase boards have a red warning sticker beside the board that states isolate main switch before removing cover, and yet they don't have them on a single phase board. I've always wondered why, so if anyone knows the answer, please get in touch. The last thing that I want to talk about is the supply side and load side of the main switch and MCB RCBOs. If we divide the main switch down the middle vertically, you will see that the line coming out of the top is the line coming out of the bottom. The same is for the neutral and demonstrates that the switch is straight through. They do not cross over. Then if we divide the switch in half horizontally, you can see that the top of the switch is the supply side in and the bottom of the switch is the load side out. If we now bring the bus bar in, you will see that the pin coming out of the main switch is the supply to the bus bar, and the pin going into the bottom of the MCB is the line in. This means that the bottom of the MCB is the supply in and the top is the load out. This should make it easier for you to understand how the switches inside a consumer unit work, and then think about where you are going to put your test probes. Because again, if you were testing and you weren't able to isolate the supply to the consumer unit, this supply side would be live. So there's no good testing there, and the load side would be dead. Obviously, in assessment situations, there would be no power to the supply side. They would never liven that up for apprentices or people in training. So you'll test at this point, but there won't be any voltage there. So be very, very careful. The Best Practice Guide 2 Issue 3 also talks about Table 53.4, which has now changed for the 18th edition to Table 537.4, although the table remains unchanged. As we look down this table, it tells you the device, it tells you the standard, it tells you whether it's suitable for isolation, whether it's suitable for emergency switching, and whether it's suitable for functional switching. It will also tell you if the device is suitable for isolation, it'll be marked with this symbol. If the device is suitable for on-load isolation, i.e. disconnection whilst carrying load, it will also display this symbol. So you're looking for 1 and 3, a main switch 60947-3 says yes, but it should display this symbol. So here we have circuit breakers to 60898, RCBO to 61009, and if we look, obviously they're applicable for isolation, emergency switching and functional switching. But the thing I want to draw your attention to here is that they are primarily circuit protective devices, and as such they are not intended for frequent load switching. Basically it suggests here that you should find alternative devices from those listed above. And this is the rest of the table. If safe isolation does not come easy to you, then please take the time to watch my in-depth video on safe isolation. If you search for Adrian Davey, AM2 or 2391, carrying out safe isolation, this video will come up. And this video aims to teach the knowledge and understanding behind safe isolation, as well as showing you the simple process of operating a lock-off kit. Once you understand the hierarchy of controls and the thought process behind safe isolation, you will not only be able to keep yourself safe, but those around you in almost any situation. Please take the time to follow the hashtag #SaferSeptember, which looks to promote safe working practices on site to keep you alive. Most apprentices are not performing safe isolation at work, which at the very least is causing them to fail the AM2 safe isolation assessment. Not only that, but it's putting people's lives at risk. By following and sharing this hashtag, it will help promote a safe culture with which you can flourish in your chosen profession. I will leave you with this final guidance from page 8 of the Electrical Safety First Best Practice Guide 2 Issue 3. I hope you've enjoyed watching, and if you like this content and want to see more, then please like, share and subscribe to get these important messages out there so that everyone can benefit from them. If we all love and care and take individual responsibility for this industry, then our everyday working world will be a much more positive place to be. Look out for the next video in this series and take care.